Good morning, this is Dr. Jingbo Louise Liu. Today is our last class. We are going to finish the chapter 13, the properties of mixtures. Particularly, we are going to focusing on the colligative properties of the solutions. Last class, we already discussed the different properties of your colloids. Generally speaking, you have two of them. One is called the Dando effect. Second one called the Brownian motion. Today, we are going to focusing on the colligative properties of solutions. So we are more based on the concentration terms and then calculate 4 different colligative properties, 4 different types of solutions. Let's recall your colligative properties. So you have 7 or 6 key points. So definition of the colligative properties, point 1. Colligative properties are the properties that depend on the number of your solute particles rather than their chemical identities. The number of particles in your solute can be predicted from the formula and the types of the solute. So you have 2 types, or you can say 3 types. One is called strong electrolyte, another one called weak electrolyte, the third one called non-electrolyte. Our equations are applicable for those non-electrolyte solutions. And then in your electrolyte, if you have the electrolyte, so they are going to be dissociated into the ions when it dissolves in solvent, such as in water. So electrolytes separates into ions when it dissolves in water. Strong electrolyte dissociated completely, otherwise weak electrolyte dissociated very small portion. The non-electrolyte does not dissociate to form the ions. Each moles of the dissolved compounds for this non-electrolyte yield 1 mole particles in your solution. So our non-electrolyte is considered the ideal solutions. When you have your non-electrolyte dissolved in water, for example, so you consider that solution an ideal solution. So we have 4 different properties. One is called the vapor pressure lowering. Second one called the boiling point elevation. Third one called the freezing point depression. The very last one called osmotic pressure. About your vapor pressure lowering, we need to know the vapor pressure of a solution containing a non-volatile non-electrolyte. We call this non-volatile non-electrolyte solution an ideal solution. It's always lower than the vapor pressure of the pure solvent. If you have a pure solvent such as water, so if you're discussing of the pressure for this solution, this vapor pressure for your solution always smaller than that pure solvent. How do you determine it? We are going to use a law called Raoult's law. Raoult's law states the vapor pressure of your solvent above your solution, this pressure of your solvent above the solution is proportional to the mole fraction of that solvent presented. So you use this equation. Vapor pressure of your solvent equals to the mole fraction of your solvent multiplied by the pure pressure of your pure solvent. The vapor pressure for your pure solvent, this P0 or P0 usually is already new. The vapor pressure lowering, the delta P is proportional to the mole fraction of your solute presented. Be careful, this mole fraction is for your solute. Vapor pressure for your solvent when you calculate it, you need the mole fraction for your solvent. The vapor pressure lowering, this delta H, called the vapor pressure lowering, is proportional to the mole fraction of the solute. So for example, so we have a solution which is composed of 10 milliliters of your glycerol, Phe3H8O3, which you dissolve it in 500 milliliters of water. This experiment has been carried out at 50 Celsius. At this temperature, your vapor pressure of your water is determined to be 92.5 torr. The density of this water is 0.988 grams per milliliter. At this 50 Celsius, your glycerol density 1.26 grams per milliliter. What's our solution? First of all, you are going to determine the mole fraction of your glycerol, the mole fraction of your water, and then you simply use Raoult's law. Before you determine the mole fraction, you need to know the grams of your water, the grams of glycerol. You use your volume multiplied by the density of your glycerol. Similarly, the same for your water. And then you determine the moles using mass divided by molar mass. And then you are going to determine similarly the moles of your water and then calculate the mole fraction. Our solution, step 1. You are going to calculate the grams of glycerol. You use 10 milliliters multiplied by its density and then divided by its molar mass. You determine the moles. On the other hand, for water, you also use the milliliters multiplied by its density divided by its molar mass. So you calculate the moles for glycerol and the moles for your water. And then determine the mole fraction of your glycerol equals to the moles of your glycerol divided by the total. Calculate the mole fraction. And then the vapor pressure lowering delta P, equals to the mole fraction multiplied by the vapor pressure for your water, 92.5 torr, which is given. So you can calculate the vapor pressure lowering, which is 0.461 torr. The second colligative property is called boiling point elevation. Third colligative property of your solution is called freezing point depression, meaning whenever you form a solution, the boiling point will be increased, the freezing point will be decreased. You are going to calculate these two values using your molality. So regarding the boiling point elevation, we need to know a solution always boils at a higher temperature than the pure solvent. The colligative property is the result of the vapor pressure lowering. The boiling point elevation is proportional to the molality of the solution. You need to use a smaller m, molality, not molarity. The reason is temperature change will result in the volume change. So therefore, you are not going to use the volume term, volume-based concentration. You use the mass and the moles-based concentration. Delta TB represents the boiling point elevation. Delta TB equals to Kb times m. This Kb represents the modular boiling point elevation constant. Is a constant value. For the different solvent, you can find this Kb for your particular solvent. Similarly, for your freezing point, you need to know A solution always freezes at a lower temperature than the pure solvent. The freezing point depression is proportional to the molarity of your solution as well. Delta TF represents the freezing point depression. Delta TF equals to KF multiplied by M molarity. KF is the molar freezing point depression constant for your solvent. KB and KF, they can be found from your handbook. They are the freezing point depression constant or boiling point elevation constant. Be careful, these two values, they are different. Do not mix two of them. And all of this boiling point, freezing elevation, boiling point elevation, freezing point elevation, freezing point depression. So I showed you this diagram corresponding to your phase diagram. So you can determine why your freezing point is going to be depressed or lowered. Boiling point is going to be increased. So you see this diagram. Let's practice some calculation about your boiling point elevation and freezing point depression. If you have a solution, you are going to add 1.0 kilograms of your isoline glycol into water. This isoline glycol is a very important anti-freezer. You're adding 1 kilograms of this isoline glycol to the 50 grams of water in your car radiator. The question is, what is the boiling point of this solution? What is the freezing point of this solution, respectively? What's our plan? First of all, you need to find the molarity of your solution, and then based on two equations, delta TF and delta TB, you can calculate your boiling point and freezing point of your solution. So first of all, you calculate molarity, and then you calculate boiling point elevation, delta TB, freezing point depression, delta TF. How do you determine molarity? First of all, you need to know the moles of your solute, which is isoline glycol. And you also need to know the kilograms of your solvent. Moles of your isoline glycol, which is your solute. The isoline glycol is the solute. You use the grams divided by molar mass of that isoline glycol. And then you are going to determine the molarity by using moles divided by kilograms of your solvent. After you determine your molarity, you calculate your delta TB and delta TF. Your delta TB equals to KB times M. Delta TF, freezing point depression, equals to Km times molarity M. And your delta TB, delta TF can be calculated. From there, you calculate your boiling point for the solution. Boiling point for your solution equals to the pure solvent plus the boiling point elevation. On the contrary, your solution has a freezing point. This freezing point will be decreased. You use the freezing point for your solvent. In this case, is water minus the freezing point depression. Our solution. Step 1. You want to calculate your moles of your glycerol. Convert your kilograms to grams. So multiply by 1,000 and then divided by its molar mass. Calculate the molar mass divided by the molar mass. You can calculate the moles. And then your molarity equals to the moles of your glycerol divided by kilograms of your water. You have 50 grams converted to kilograms divided by 1,000. So you determine the molality. Delta TB, boiling point elevation equals to the molality multiplied by the freezing point elevation constant. This constant value is 0.512 Celsius per molality. You determine the boiling point elevation. And then the solution has a boiling point equals to 100 plus 1.85. This 100 Celsius is your boiling point for your pure water at 1 atm. Just assume your pressure is at 1 atm. Similarly, you calculate delta TF, freezing point depression. Freezing point depression equals 3.62 times by the constant value 1.86 Celsius per molality. This value called the freezing point depression constant. You calculate it, which is 6.73 Celsius, and then you use your water freezing point minus this freezing point depression to calculate your freezing point for your solution, which is negative 6.73 Celsius. That's two different variables, two different colligative properties. One is called boiling point elevation. Second one called freezing point depression. The very last one is called osmotic pressure. We need to know several key points. First of all, the osmosis. Second one, osmotic pressure and its calculation. Third one, how this osmotic pressure has been developed. Osmosis is the movement of solvent particles from a region of the higher to a region of a lower concentration through a semi-permeable membrane. Your solvent moves or flows from a more dilute solution to a more concentrated one. Be careful, your solvent moves in the reverse direction. Osmotic pressure is defined as the pressure which need to be applied to prevent the net flow of your solvent. This osmotic pressure equals to the molarity times ideal gas constant times temperature in Kelvin. MRT. M represents molality, moles per liter. Capital R represents ideal gas constant 0.08216 atm liter per mole per Kelvin. Temperature must be in Kelvin. The reason for this osmotic pressure. So we are going to do this experiment. You have a U-tube. In the middle of the U-tube, you place a semi-permeable membrane, meaning you only allow a certain particles to pass through to diffuse. And then you put your solution on one side, your pure solvent on the other side. Your solution on one side, your pure solvent on the other side. What's going to happen? So your pure solvent is going to move through this permeable membrane, actually through two ways, until a certain point. The net movement of your pure solvent to this right-hand side, because your solvent wants to become the same amount. Yeah, you can say the same amount. Therefore, so your solution is rising up, your pure solvent surface decreasing. You are going to see these differences these differences in height. Also, this difference represents a pressure. This pressure is called osmotic pressure. Osmotic pressure occurs against your atmosphere. So therefore, you want to prevent this pure solvent movement, you need to apply this osmotic pressure. So in this case, this pressure applied is called osmotic pressure. The pressure applied to prevent increased this solution from rising up. So this is called osmotic pressure. So in your osmotic pressure at the beginning, you have the rate of the movement. So the rate into your solution and the rate out of your solution. So the rate to this solution, the rate out of the solution. You need to see in the beginning, the rate in the solution into the solution is higher than the reverse order. So at a certain point, the rate into the solution and the rate out of the solution, your solvent move into the solution, move out of the solution when this rate is equal to each other. So this condition is called, you can say reach the equilibrium. And you want this pressure to be applied. You want your this solvent, this pure solvent, move out of your solution. So the rate out of the solution, and the rate in the solution, if they are reversed, so you apply this osmotic pressure. Let's see an example. We want you to determine the molar mass based on the osmotic pressure. The problem is, a biochemist have been discovered more than 400 mutant varieties. So in your hemoglobin, the blood protein that carries your oxygen, a physician dissolves 21.5 milligrams of one variety of this mutant, and then you prepare a solution by adding into about 1.5 milliliters of water. This research has been carried on at 5 Celsius. And then you measure your osmotic pressure, which is 3.61 torr. The question is, what is the molar mass of this particular protein? What's our plan? In order to know the molar mass, you need to know the grams. So you have 21.5 grams. Convert milligrams to grams. In order to know the molar mass, you also need to know the molarity. How do you determine molarity? So from this osmotic pressure, so you can determine molarity. Osmotic pressure equals molarity times RT. Therefore, you calculate your molarity. From this molarity, you can calculate the moles. Using mass divided by moles gives you molar mass. That's our plan. First of all, you are going to do the unit conversion. Convert your 21.5 milligrams of your protein, 2 grams. Convert your 1.5 milliliters to the liters. Convert your Celsius from 5 Celsius to Kelvin. Convert your torr to atm. That's our first step. Second step, you calculate your molarity, and then you calculate moles, and then you determine the molar mass. Let's see. Our molarity equals to the osmotic pressure divided by RT. Osmotic pressure 3.61 torrs converted to atm. You divide it by 760. And then use your ideal gas constant multiplied by the temperature in Kelvin. So my calculation for the molarity, so 2.08 times 10 to negative 4 mole per liter. And then you are going to use this molarity multiplied by your liters. So convert your milliliter to the liters. So you have your 1.51 milliliters convert to liters. And then you convert your milligrams to grams. You use your grams divided by your moles. Grams divided by the moles give you the molar mass of this protein. So I will give everybody 2 minutes to do this calculation. First of all, convert pressure to atm. Second, convert temperature to Kelvin. Third one, convert your milliliters to liters. And then calculate moles. Convert your milligrams to grams. And then calculate your molar mass. Molar mass, again, equals to grams divided by moles. This is about our colligative properties. The above calculation is assuming your solution is non-volatile, non-electrolyte solution. If you have a volatile non-electrolyte, so you are going to consider both solute and solvent. In this case, we are not going to require our students to do the correction. You are not required. But be careful. Whenever you have the volatile component lowers the vapor pressure of the other. Since one each other, they are going to lower the mole fraction of the others. So in this case, for your solution, the vapor pressure will have a higher mole fraction than the more volatile component. So again, this one, we are not going to require you to know it, but you need to know there is some differences. Another solution is called strong electrolyte solution. If you have your strong electrolyte, this strong electrolyte dissociated completely into the ion forms. So in this case, you are going to calculate a 1/2 factor to do the correction. Assume you have your formula. You assume this formula is the expected particles such as sodium chloride. You assume you have 1 mole of sodium chloride. That expected value, assume sodium chloride is not volatile, is not an electrolyte. In that case, this value will be 1 mole. However, your sodium chloride is going to be produced 1 mole sodium, 1 mole chloride, totally 2 moles of ions. The measured value will be 2. The 1/2 factor will be equal to 1 plus 1 divided by 1. You have 2. In this case, your 1/2 factor will be taken into consideration when you calculate the above 4 different properties. Your vapor pressure lowering, delta P, will be equals to I 1/2 factor multiplied by mole fraction times the pressure for your pure solvent. Similarly, delta TB, boiling point elevation, you also need to multiply by 1/2 factor. The freezing point elevator multiplied by 1/2 factor. Similarly, vapor pressure equals I multiplied by mRT. So this is how you calculate the colligative properties of a solution composed of a strong electrolyte. If you have non-strong electrolyte, this is something else. Last class, I believe we already discussed about these different colloids. You have aerosol, another aerosol, 2 types of aerosol. One is a liquid dispersed in gas, another one is solid dispersed in gas. You also have 2 types of forms. You have 2 types of emulsion and 2 different salts. I will ask our students to recall these different types of colloids. And also in this table, I listed the different commonly used solvent. It's boiling point, it's a Kb, and it's Kf, constant values. So you can do the calculations based on these values. And their boiling point and the melting point. Melting point is the same as your freezing point. From there, you can calculate a boiling and freezing point when you form a solution.